Welcome everyone to the by now fourth tutorial of the deep learning course. Today we will talk about optimization and initialization, two topics you have already seen in lecture 3. And here we will discuss them also, how you can actually implement them, how you can test, for example, different initializations, optimizations, how do you see actually which one is better. And you just see it here in PyTorch code, so you can actually play around with it, see the effects if you, for example, initialize the network poorly. Again, you can just run the notebook by going to our tutorial webpage and then opening here the Google Colab. Alternatively, you can of course just look at the website. We also have a few math derivations in here, so maybe for this the website is the easier way to access them. We will start again, so we will structure this notebook into two parts. First we look at initialization, and then we will look at optimization, using actually also the initialization we have seen then before. The first part we have here again is the standard way as you have seen in the previous two tutorials. So we have first a few libraries to import, including here PyTorch. So let's do that first. Of course, again, run the notebook anyways. Next we also have again our paths we define, so for our data set where we want to store it, and the checkpoint path where we want to store our trained models. The data path, make sure it's the same as you had in tutorial 3 in case you run it locally, because we will use the same data set, so you don't want to download the data set twice here. So let's do this as well and check if you're on Google Colab that you actually have here the device of a GPU, otherwise change your runtime environment again. In this cell we will again download pre-trained models, so we have a couple of them here, and as you already see we will have here different models trained again on Fetch and MNIST, but using different optimizers. So we will look here at SGD, SGD with Momentum, and Atom as the three competitors. So let's do this here as well, so we don't have to train our models from scratch. As I said, we will use Fetch and MNIST as a data set. You see that this is basically exactly the same code as we had in the tutorial 3. One difference, however, we use different normalization constants here. So previously we had 0.5 and 0.5, right? So this basically took an image and scaled it between -1 and 1 as values, while here we now actually make sure that the mean of all pixels is 0 and the standard deviation is 1. Why do we do this? This is basically, this is very important if you do initialization, because there we take the assumption that our input has a 0 mean and a standard deviation of 1, while actually you can still achieve good results if you just map it between -1 and 1. So we do it here explicitly because it's actually slightly more better in theory, and it also just shows us how we actually can do good initialization. So let's import and eventually also download our data set here. On Google Colab we of course download it again. To get these parameters up here to calculate the normalization, you can also just take the data set. So the data set, take the data, and let's calculate the mean and the standard deviation of this data. And there you will see that we actually get exactly the values we have up here, or slightly different, depending on our approximation. And then we can go down here, and if we load a batch, we should hopefully see exactly that the mean is very close to 0 and the standard deviation is very close to 1. But you also see that now the maximum pixel value is 2, while the minimum is -0.8. This is because Fashion MNIST, or MNIST in general, has a lot of black pixels, right? So it actually has a bias towards the negative side. This is why the maximum values are actually larger here. We will also use here our base network. So the network we also used in tutorial 3, which is just a linear neural network with a couple of hidden layers, which we use then to analyze the initializations, also optimizations. So there's nothing different if you know it from the last tutorial, except one thing. Instead of an n.sequential, we now have here a different part of PyTorch, which is called nn.modulelist. And the difference is that nn.modulelist explicitly saves these modules as a list. So we can access with self.layers as a list. In this list are then the separate layers, and we have to then execute them in a loop. We do this here because we actually need to access each layer independently. This is just depending on what you need. You can use the different functions. So let's also run it here. Finally, we then have here again a dictionary for our activation functions, because we will try a few different ones. One we define here is what we call here identity. So meaning this is actually an activation function which doesn't have any effect. So it's a linear mapping from the input to the output. We could also use different functions. So if you do, for example, n.sequential without any inputs, it is basically this identity function. Of course, this is not an activation function you should use in a neural network, but we will use it to analyze then our initializations. So we will first start to assume we have a network without any activation function, which makes our job easier to actually analyze what is going on. And then we introduce the activation functions in a second step to see how we actually have to adjust our initializations for that. So let's also just do it here. In the next cell, which is a bit larger, as you can see, we define different functions for visualizing things. So we have here then a function for visualizing the weight distribution. So we take each linear layer and plot just the distribution of the weight parameters we have in there. So we don't use the bias here, just weights. We also visualize the gradients. So a function which you have seen in the previous tutorial, we put a batch through the neural network, calculate the loss, backpropagate, and visualize the gradient distribution over the different parameters. And finally, we also want to visualize the activations, meaning that if we take a batch, run it through the network, actually visualize what is coming out of the linear layers. This is quite important here because we want to check if they are basically the same or what are the values here. So the specifics for these visualization functions are not too important. If you're interested, please take a closer look. So now we can start with the initialization. Of course, so this is not the only blog post about initialization. Once you have gone through this one, I would recommend you, if you still have questions like in general, what is initialization, I didn't really understand it, maybe look at here the deeplearning.ai blog post. If you think like, okay, I need to understand the math more in detail, then check maybe this blog post, which goes through all the derivations quite nicely. So we will start here, as I said, with a base network we have up there, and use identity function as our activation function, because we then assume, okay, we first don't have any, and then let's check how it actually works with activation functions. Let's create it. Usually it takes a little longer now because it also has to push first to the GPU, and therefore we can just wait for it. The first initialization we will look at is what I call here the constant initialization. So let's say we have a neural network. What would be the easiest initialization? How about we just initialize each weight parameter with the exact same value, different from 0. So you already know it doesn't really make sense to initialize everything with 0, because then the output is always 0 and we will not have any gradients. But what if we actually just set it to a random constant value? So here I will define an initialization function. So we will use different initialization functions here all the time, where I basically go through the parameters and say parameter.data.fill c. So that means nothing else than taking the values of the parameters and setting them all to the value c. This underscores again the in-place operation, because we want to use the same memory. We don't want to do any computation graph here. So what happens if we just, for example, initialize it with a small value like 0.005? This we can run here, and we plot then the gradients and the activations. The gradients you already see, these are not looking good if you do that. So the output layer has a gradient magnitude here between minus 0.5 and 0.5, which is quite large, while the other ones here actually have no variance at all. So all the weight parameters have the exact same gradients in these hidden layers in between. And this already shows you we can't learn from that. So if all weight parameters have the exact same value and the exact same gradients, they will always be the same. So this is why a constant initialization already doesn't work in terms of how we train it, and therefore we can already discard it. So what we know is we can't use a constant initialization, we need something stochastic. The weight parameters need to be different so we can learn at all anything. What variance, for example, should we use? So it's obvious it is usually better to use a weight mean of 0, just because everything should be zero-centered in our ideal world, while the variance is not clear. So what should we actually use? And here, let's maybe just start with experimenting with different initializations. So let's, for example, set it to 0.01 and check how actually then the activations look like. Because what we want is that the network has two parts, so that the activations actually have a similar variance. This ensures us that we are always using the activation function quite nicely. And as you can see here, actually, if we use such a standard deviation, then we go from -1 to 1 to actually here an input of -0.025. So the last layer which is applied on this output, you can see it doesn't really get good features to distinguish which input has been already in there, because all of them are close to 0. Therefore, we can't really train a network, or we have very big problems in training. If the activation distribution, so if the variance of the output of the activations getting smaller and smaller here. Of course, easy fix. What if we just use larger standard deviation, so use 0.1 for our network here? Then we see that it actually has a different problem. So if you use too small, you see that you actually converge to 0. If you take too large, you go the other direction, meaning that you actually explode. So you see we have already -10 in the beginning, and we go here to -50 with a variance of over 300. That is also not what we want, because if we have, for example, a ton h, it basically maps all the values here directly to -1 and saturates for all of them, so meaning we don't have any gradients, and then we again can't train our network. You can now play around and say, what about 0.05, 0.02, and so on, but you will see that you actually can't find a value for which the variance across these activations stay exactly the same. And this is because we will check it out below, namely that it depends actually on your size of a hidden layer. So let's start with how can we actually find appropriate values to initialize. As I said, we want two things. As our activation functions, we have designed them to work well on a zero-centered way, and of course we want the variance to have still some signals as the input layer, and therefore different features. If the features don't have any variance, then we can't learn anything. Therefore, we say these two are our requirements, and let's say we have here a simple linear layer, where basically y is the output, w is the weight matrix, x is the input, b is then our bias. What we now want to see is what is actually the variance of a weight matrix we have here, such that the output variance is equals to the input variance. Because if we can make that sure, then we know that all the activation distributions are what we actually want it to be. How we now approach it is by first saying, okay, we can actually ignore the bias, because we said we want to have a mean of 0, right? So let's just say we have a weight mean of 0, and we have a bias of 0. This is also because we say that x, which is the input, we now assume it has already a good distribution as we wanted. So it already has a mean of 0 and a standard deviation which is large enough. And now we want to basically say, okay, how can we calculate the variance of the weight parameters we need? And this we can do here. So basically I said, okay, for this single output we know that yi is calculated by the sum over j of w and x, right? So it's basically just this one line, one element in the matrix multiplication. And if you do now the calculation of what is the variance of this one, which we want to be the variance of the input of x, right? You can go through all this derivation, which is not too complicated, but basically what you get out of here is that our weight standard deviation should be 1 divided by d of x, where d of x is the number of input neurons. This is because you see here we have a sum over j, so a sum over dx elements. All of them are independent. That is the assumption we take, because we say the features are relatively independent and has all basically the same variance. And then we can say, okay, variance of xj we know is basically here the variance, and therefore we get this result by just changing dx on the other side with a standard deviation. So that's actually a quite simple and easy solution we have, and let's maybe try it out here. So the equal var init is basically the initialization where we now use 1 divided by d of x and would expect that the output distribution is the same as the input distribution with the same standard deviation. So let's say if we have a bias, we fill it with 0. If we have a weight parameter, this is the other case, initialize it with a standard deviation of 1 divided by the square root of dx. So basically, with the variance, we put in here the standard deviation. So let's also plot this. And we would, of course, now hope that it's much more stable than the previous two initializations we have seen. And now we can actually check and see that it's actually exactly very stable as we wanted. So let's maybe wait until also the activations are plotted. And here you can see, or especially if you look here at the variances, you see that we're actually almost perfect always at 1. If we push one batch through, the activations have always the same standard deviation and the mean, and that's exactly what we want. So that's of course very nice, but now we come to the second part. Well, we have assumed the identity activation function, right? So this is something we have to change, but before that, we also have a second thing we need to change, namely that we have an activation distribution, which is nice, but the counterpart is also we want the gradient distribution to be nice, right? So we actually want that the standard deviation also across gradients, across the layers, is in a similar range, because this makes it easier for us to use optimization algorithm like SGD, where we have the same learning rate for each layer. If we have very different standard deviations, we don't can find actually a good learning rate which fits all of the layers. This is why this is basically the counterpart to the activation distribution, that we want the gradient distribution to be also very similar. And if you do the calculation, which I don't do here just for simplicity, you actually come to the same result. So it is actually very similar. Feel free to do it or just read it up in the blog post if you're interested. If you do it the other way, you get out that actually 1 divided by d of y, so basically the number of output neurons, should be what we should initialize our network with, so we have a nice gradient distribution. And this you see, basically we can't achieve that both the activation distribution and the gradient distribution is the same for any neural network. And this is why what we usually do, or what Benju et al. Also proposed in 2010, was the Xavier initialization, which basically takes the harmonic mean of both. Therefore, we basically take a compromise between taking d of x and d of y, so basically the gradient distribution and the activation distribution, which usually also works well. You can do it either in a normal distribution, or you often see also in a uniform distribution that you sample the weights from. This is actually often done, and it just has this small benefit that you can't have these extreme weights, right? So you have an upper bound for the weights. Well, if you're very, very unlucky with a normal distribution, you could actually also sample a very high weight, but this is not a big difference usually. So let's also implement it here. You see we just changed a little bit the bound. So we now initialized here with a uniform one with this variance, and let's do it, and hopefully we should now see that we actually have a compromise between the two of activation distribution and gradient distribution. We are not able now to do both perfectly. That's of course then a drawback, but it's usually still good enough to have a very nice optimization. So you see here, for example, activation distribution is relatively equal, although the output layer here has a much higher variance. This is because of a mismatch of hidden sizes. So we started here with a hidden size of 512, up here we have 128, and map it to 10. And there you see that actually dx and dy are then very different, 128 and 10, and this is why we get a very big difference here actually, which is not too bad. It's still okay. You see then the gradient distribution is actually also quite nice. Start just with 0.05 and goes also again with the last layer is quite different. But this is just one layer and this is the output layer, which is usually still fine. So in the previous part, you have seen now how you can initialize a neural network based on a network without activation functions. What happens if we now introduce activation functions? So the first activation function we can look at is tanh, because tanh was also the activation function with Xavier initialization was originally proposed. And this is why you can take the assumption that the tanh is similar to a linear activation, so as the identity around 0. So actually at 0 it is perfectly the same, but we have also that the initial features are close to 0, and this is what you use here as assumption. So if we now take a tanh neural network, just initialize it with Xavier initialization, you see that it usually works quite well. So this is why you often see that tanh neural networks are also then initialized with the Xavier initialization. You see again, of course, the last one, the last variance here for the gradient magnitudes is higher because of a mismatch as we had before, but also the activation distribution is quite similar. It decreases a bit, yes, as you can see, from 1.1 we go down to 0.24, 0.25. But this is because we start here actually with a higher one, so between -5 and 5. But once we reach something like -2 and 2, we will not get very different results, because at this range, the tanh is quite similar to a linear unit. So you will have a decrease in case your initial standard deviation is high, but this one doesn't go to 0. It will go to a value like here, 0.25, which is still sufficient for very deep networks. Tanh was easy. What about ReLU? ReLU is now a little bit more difficult because ReLU is not linear itself, so it's not very similar to linear, and it actually has this point at 0 where we change the negative values to 0, right? Therefore, also the expectation we get out of a ReLU network is not 0, and we have in our initial discussion we actually assumed it to be 0. For this, you need to take a few steps, extra steps that are listed below. So basically what we have done before is to say that the variance of w times x is variance of w times variance of x. This is now not true anymore, because the expectation of x squared is now not just the variance. But the difference we now have here is to say, okay, what if actually x is the input of a previous linear layer, right? So let's say x is already the output of a ReLU, which I define here. So y tilde is basically the output of a previous linear layer, which has then been pushed through ReLU, which is then called x. And what if we actually try to calculate it then for the expectation? Then you see that we actually get out that the expectation of x squared is 1/2 of a variance of an input to the ReLU. This is because the ReLU is symmetric, so it basically creates a symmetric, let's rather say, so y tilde is basically a distribution where we again assume it has a 0 mean and is symmetric around 0. Therefore, if you take all the 0 ones to half, you actually just can say, okay, it's half of expectation of just the positive side. And this is what we do here and get basically this 1/2 factor. Again, this is just roughly explained in mathematical terms. Derivation, feel free to look at the paper, also read just the tutorial in a bit more details. So what we have to encounter this 1/2 as a factor, and that we can just do by scaling our initialization by 2 for the standard deviation. And this is called the Kaiming initialization, as you find here. So what we do is to say if it's a bias, then fill it with 0. If it is the layer 0, there we actually have one difference, namely that the input to this first layer is not a value, right? So this is not the output of a value. This is why we don't take the factor of 2. While for the second one here, we actually do it with the square root of 2 because we have a standard deviation. And this we can also perform, and you will see that it is actually exactly like we wanted to have it. Just notice that the Kaiming initialization originally proposed is that it uses just the dx, so that has this same activation distribution over the network. This is because in the paper they argued that actually if you just focus on the activation distribution, you will get a similar or good enough gradient distribution. Also at this time already Adam was proposed, and therefore Adam already helps you to have a bit encountering these different gradient distributions. So usually a Kaiming initialization just focusing on dx is also working well. As you can see here, the dx for activation distribution is quite constant, while then the gradient distribution differs slightly because that we just focus on dx. So this is now everything for the initialization. One last part to notice is what if we have different initializations like a leaky ReLU. There PyTorch can help you out. So you see that we have actually here the factor of the square root of 2, or here 1 divided by 2 for the variance, right? For different activation functions, PyTorch provides a functionality called torch.nm.init.calculateGain, which basically calculates for you this small factor you need to have to actually adjust your initialization for the specific activation function. And this is why it basically is quite simple to also use, for example, leaky ReLU and design a specific initialization for this network. In the next part, we will now look at the optimization part of this node.